Are you speaking?
Sir, just so you know, your mic's not on.
Yep, yeah, I know. I didn't have it on yet. Can you hear me now? Hello?
Oh, yeah. Yep.
Okay, give me just 1 second here. Yeah, my mic wasn't on yet. I only was doing like a quick run. However, I still don't see like my mic working like on the actual app. But if you can hear me, can you hear me loud and clear?
Yes.
Okay, perfect. Glad to hear that. Okay, so we're going to get started. So today we're going to tackle three-phase rectification. That's what we're going to be moving into. So just give me 1 second here, finish setting things up. Okay, perfect. So now we can begin. Okay, guys, so today we are going to get into three-phase rectification. And what we are going to do in today's class, we are going to discuss why is it that most of the industrial systems out there use three-phase rectification rather than single-phase rectification. Okay, so for this, of course, we are going to be using diodes, but we got to keep in mind that when we saw the single quad and four quad, okay, like DC controls, those quads were using, do you remember what device they were using? Instead of just diodes? Something that have a gate? Anyone can remember that?
SCR.
Pardon me?
The SCR.
The SCR, which is the silicon controlled rectifier. Okay, so as we move forward now, we are going to get into three-phase rectification. And also now we are going to be moving into the fact that the smoother way to get a DC signal output is using 6 diodes rather than just using 4 for a single phase rectifier. So right here on this, picture right here at the bottom, we have a half-wave rectifier. So our sine wave, okay, so we got to keep in mind that our sine wave, okay, this part of the sine wave here is positive. That part of the sine wave below ground. So this black line here represents the ground or the neutral plane. So we have the above the ground signal or pulse, and below the ground signal or pulse. So we have a positive signal and a negative signal. In the case of the diode, we must remember that this side of the diode, this region here, is the positive side, which is called the anode. And this other region here is called the cathode, which is the negative side of the diode. So now when we feed a positive pulse to the positive side of the diode is going to become forward biased. And the diode is going to become a closed switch or a conductor. That's why we have half a pulse going through it. Okay, so something that I have seen sometimes is that the students tend to get confused and they connect the diode backwards because they think that because we are getting a positive pulse here, that we are supposed to connect the anode to the positive side. I mean, to the positives that we want to create, but it's the complete opposite. We connect the positive side of the diode to the power source. That's another way to say it. The positive side of the diode always go to the power source. That way, the positive side or the positive pulse of the power source will be conducted through the diode. And of course, it has to come out from somewhere. So it's got to be coming off that negative side. If you want to think about it, like the positive, which is holes, are going to be attracted to the negative, which is an excess of electrons, and that's what's going to be conducted. Okay, so this negative here is not creating a negative pulse. This is just like a vacuum, if you want to think of, it is just attracting all the holes to the negative region, thus creating a positive output voltage to the load. Did I make it too confusing, or that kind of makes sense? So far, so good. That's the advantage of being in the classroom, to be honest with you. I don't see your faces, so I don't know what you were thinking. So anyway, well, I'll just keep moving. We'll just keep moving along if you don't have any questions or comments. Any comments, though, or questions?
No.
So far, so good. Now, however, when we have a three-phase rectifier, in this instance, still we have the same thing. We're going to be feeding our three phases, line one, and it's very important that when you are doing your project, you distinguish that line one has to be a red wire going to the diode. Line two has to be a black wire. That line three has to be blue for sure. Okay, why? Because the color code indicates that red, black, blue is three-phase. Now, your red, black, blue is going to be feeding your load. And we have a center tap Y connection. We have a connection, a Y input with a center tap. And the center tap is going to be, like in this case, our negative terminal. Okay, that center tap from the transformer is going to be your negative terminal, while the positive side is going to be what's coming from your diodes. Like in this instance, each one of these diodes is going to conduct half a wave, okay? So let me show you that here. So each one of the diodes is going to be conducting half a wave. So under regular circumstances, okay, so we are going to say, and we are going to see that right here at this point, we have, let's say, 0 degrees. Remember that we have mechanical degrees and we have electrical degrees. So from at that point, we have 0 degrees or 0 electrical degrees. As we move along, right on this point here, we have 180 degrees. Give me 1 second here. Excuse me, let me delete this. I don't want this to be confusing. Okay. So I'm gonna put it in the following way. So right here, again, we have 0 degrees. Right here, we have up to this point, 120 degrees. Right here, up to this point, we have 240 degrees. And up to this point, we have 360. You may wonder why. If we had a single phase system, in our single phase system, right at this point here, we would have 180 degrees. So when we have a single phase system with full wave rectification, we have a signal that starts right here. It collapses to 0 at this point, and that's going to be line 1. And then it goes back up, and it collapses back to 0, and that's going to be line 2. However, this signal is always collapsing back to 0, causing that our average voltage is going to be equal, the E average is going to be equal to the input voltage, which is, let's say, like in the input voltage was going to be 120 volts. So we are going to multiply by 0.9, okay? And that is for the purple lines that we have in there. And that's going to give us the average voltage, bless you, whoever that was. However, when we have a three-phase system, it is important to note that the output DC, as I am outlining here, never drops back to 0. Okay, so like in that instance, like if the rectifier voltage, like we have 2 examples here, like if the voltage that we need to rectify was equal to 208 volts, then the output voltage would be equal to 243 volts approximately. In order to do that calculation, okay, like my recommendation is, even when in this PowerPoint we have like an example of 120 times 1.169, what we are going to be using, I mean, that's exactly what we're going to have. Like if we were going to have like 208, for simplicity's sake, we say 1.17, okay, instead of 1.169. So 1.17 is going to be the multiplying factor that we are going to use for a half-wave rectifier. Why that's happening? Because instead of having just 2 pulses, now we have 3 pulses that are coming, like this first pulse here. That's going to be coming from the first phase. Okay, so this is going to be our red. The second phase is going to be this other pulse here, is going to be the black. And the third phase is going to be our blue. So every 360 electrical degrees from this point to this point, we are going to have, instead of 2 pulses, like in the case of single phase, which is represented by the purple marks, we are going to have 3 pulses. So you can see that our average voltage, you can see this line here, never drops back to 0. That's supremely important because that's what causes this average voltage to be higher than the RMS voltage. I want you to keep in mind that this 120 volts here, even when we are using the RMS voltage, this is RMS, not peak, okay? This is RMS. However, the peak voltage of 120 volts would be 170 volts. So whenever you use 3-phase rectification, you would be able, as you can see, like your output voltage is going to be closer to the peak voltage. Like in the case of single phase, okay, it's going to be like below the RMS voltage. Why? Because we are only able to use 90% of the feed voltage. However, in the case of 3-phase, we are able to use, for a half-wave rectifier, 117% of the input RMS voltage. But it's not that we are creating energy. The reason why we can use 117% of the input is because in reality, we have, as for peak voltage, 170 volts. So we are getting closer on the DC output to that peak. that we would completely be able to do if we had the right amount of capacity. Any questions about that?
Where'd you get 120?
So the 120 is just an example, right?
Yeah, that's just an example, okay?
Okay,
So the what you have in the question, like when you see like if the rectifier in this example is connected to 208, so that you're just applying that 208 times 1.169, which is giving you 243.2, correct?
Perfect, perfect. So, and I hope I didn't confuse you, because here in this question, it says 208. Here we have 120. So it's just like two different voltage. And it's the same equation. Either you apply 208 or you apply 120, and still it's going to be the same equation. You are going to multiply any value, any input RMS value is going to be multiplied by 1.17, which is what you have in your table. Kind of make sense? Yeah. Yeah, perfect. Okay, so let's keep moving then, guys. Okay, so on this on this new slide that we have, then we have a full wave rectifier. So now, instead of employing just 3 diodes, we're employing 6 diodes. So if you think about it, the difference between like a single phase bridge rectifier and a 3-phase bridge rectifier is that in the single phase bridge rectifier, we are using 4 diodes. While in the 3-phase rectifier, because we are going to be using 3 input lines, line 1, line 2, and line 3, we are having an additional branch right here of diodes. So if you think about it, we could do the following. We could say that the very first set of diodes, the very first branch is line 1, as you can see in there. The very second set of diodes is line 2. And the third branch of diodes is line 3. Each one of these diodes is going to be providing, okay, so you can see that like the 3 diodes are connected in order to produce a positive pulse. Okay, so each one of these lines is going to contribute a positive pulse. Okay, and each one of these diodes then are going to recapture this positive pulse, so it can be distributed back. You know, like in the case of the first branch, is going to capture whatever signal it can capture, and that those electrons are going to flow back into line 1, line 2, or line 3. Now, when we have 6 diodes and we have a bridge, like a 3-phase bridge rectifier, then we get a surprise. We get a pleasant surprise in that instance, because we get a very smooth output signal in such a way, okay, that, and okay, even when we have here in the PowerPoint, like 2 different values, I just want you, so you don't get confused, to concentrate on this one here, okay? So this is going to be equal to the average value, excuse me, is going to be equal to the RMS input times 1.35, which in other words is pretty much like 95.5% of the peak voltage, and that is just amazing. Okay, so in a single phase rectifier,
So is all this going to be like uploaded onto Econestoga so we can look at it again?
it's only, oh, you mean like the
This presentation.
Oh, I can like copy the, I'm not gonna be updating anything, but by all means, I can copy the link from Zoom, and so you can watch this again if you need to.
Yeah,
That's
I'd
not
like
a
to
problem.
go over this again.
Okay, perfect. Yeah. So anyway, so what I was telling you here, guys, so I want you please to remember that when we are trying to calculate the average of a single phase, okay, this is important, single phase rectifier, we have that peak, okay, we are gonna have peak times what? Remember that magic number, that magical number? $6.37, remember that number? In other words, with a single phase rectifier, we only get 60, roughly about 64% of the peak voltage. That's the amount of output that we can get with a regular single phase full wave rectifier. However, when we have a three-phase rectifier, we pretty much get 96% of the peak voltage. That's the amount of average output that we are going to get, which is pretty amazing.
So is this
So
better because then you wouldn't really have to use a capacitor if you needed the more?
perfect, perfect. So the advantage is that if you wanted to go to the peak voltage, if you want your signal to be completely flat because you need to, let's say, like you need to control some kind of a delicate component, then you can use a thinner diode and you can use a minimum amount of capacitance and you are going to be able to get perfect DC. Because you only have to worry about having to filter a very minimum amount of ripple voltage. As we can see by this ripple that is left on this signal. Did I answer your question?
Yep.
Okay, thank you. So now I want you just, I want you to be able to see like the comparison now between the signals whenever we apply capacitance and whenever we filter or signal. Okay, so in the case of a single phase half wave, we are going to have to filter like this huge gap. So we would have to employ to the load a very large capacitance in order to be able to filter the ripple, which is going to be created by this signal. So we have a lot of ripple. So for the same purpose, for a single phase full wave, we are going to have to employ less capacitance because now instead of having just half a wave, we have two full half waves. And that's why, because we have two full half waves, like this half wave here is coming from line 1, this other half is coming from line 2, and they alternate. So line 1, line 2, line 1, line 2, and so on and so forth. While in the case of the half wave, it's only line 1 all the time. We don't have a line 2. We only have line 1, and then nothing, line 1 again, and then nothing. While here, we have line 1, and then line 2, and then line 1. So the total average voltage is dramatically improved. When it comes to the three-phase half-wave rectifier, that can only be done with Y-connected system, because in the three-phase half-wave, we need a return point. In this instance, we are going to have here line 1, line 2, line 3 for a 360 degrees cycle. However, all this is going to be returning through the common point, okay, which is going to be our center tap in the transformer. However, you can see that it's still here, we get some kind of a ripple. It's an improvement over the full wave single phase. But when we really want to reap the benefit of rectification, we have to go with the three-phase full wave rectifier. And in this instance, we can connect the three-phase full wave to either a Y system. Okay, so the input can be either Y or the input can be delta. So what's going to be the difference between the two? That in the case of the Y is like having a series circuit, okay, a series input in a sense. Because if we were going to have like 120 volts, let's say that that is the phase voltage, okay? If phase voltage is equal to 120, phase to neutral is going to be equal to 120. However, the phase to phase voltage, if this is line 1, this is line 2, the center tap here is the neutral. If the voltage between line 1 to neutral is 120, the phase to phase is going to be equal to how much? Do you remember how much? 120. Pardon me?
208.
Perfect. It's going to be 120 times the square root of 3. Why? Because, why the square root of 3 and not 2? Because the out of phase component between line 1 and line 2, it's only 120 degrees. It is not the full 180 degrees. Here, the out of phase components between line 1 and 2, which is in the single phase, it is equal to 180. However, here, the out of phase component between the lines, okay, between this phase and this phase, we only have 120 degrees out of phase component. So that's why that the total voltage is going to be equal to your line voltage, which is line to neutral, times the square root of 3, which is like that 1.73. Now, if we have a delta system, and in a delta system, we have 120 volts, okay, and that is the phase voltage. In delta is like a parallel circuit, okay? It's like having all the windings, all the transformers making the parallel connection, not the parallel, excuse me, the delta connection is like if we have all of those windings, all of those transformers connected in parallel, okay? So in this instance, phase voltage and line voltage is gonna be the same. Because this on the top, if this is line 1, and this is line 2, voltage is gonna be 120. We don't have, in that instance anyways, like a center tap or a neutral where we can go back with our, I mean, like we could create, okay, so you know, we could create a center tap if we wanted to, especially when we have like an open delta. But in reality, in delta, we don't really have like a neutral per se. Okay, so anyways, like the advantage of the three-phase full wave is that we are going to be able to use either or. And what's going to be the difference between the two? Here, depending on the amount of output voltage that we need, with this Y input, we are going to have a higher output voltage on the rectifier. But with this input, which is the Y1, excuse me, the delta input, then we are going to have a higher current output. So it just depends on the application. So let's keep moving. The devices like motors and solenoids will operate very well with pulsating direct current. But other devices like computers, VFDs, and everything else, in order to properly operate, they are going to need filtration. Because of that, when you need to rectify your voltage, when you rectify your voltage, believe it or not, yes, you are going to be using like a capacitor, and the capacitor is going to be able to filter the ripple voltage but also you are going to use a short coil. Okay, you are going to be using a coil which is going to be connected in series in order to be able to rectify also the current. Oh, this is going by itself. Okay, so let's keep moving, guys. So the inductor, this is a very, very important detail. I want you please to keep in mind the inductor or choke is connected in series with the load. Inductors, they oppose a change in current. That's one of their main characteristics. So what's going to happen is that the current is going to rise. The inductor is going to be opposing that change in current, but the inductor is going to get magnetized and it's going to be producing, of course, a current. Okay, it's going to be producing like a counter EMF, and at the same time, as soon as you get magnetized, when your current started to collapse, then the inductor, the collapsing magnetic field on the inductor is going to produce a current in the same direction of the applied current. And because it's opposing a change in current, it produces a current that tries to keep the load energized and try to keep the load from collapsing its current back to zero. You got to keep in mind that in a rectifier, you have both. You have a voltage component and a current component. The current component is going to be rectified by the choke, which is connected in series to the load. While your voltage component, okay, so your voltage component is going to be rectified by your capacitor. And it's going to be the same idea. In the case of your voltage component, the capacitor is going to charge. And when the signal is collapsing back to zero, the capacitor is going to discharge across the load. And that way, you are going to be able to get that type of signal where you have like your capacitor charging to this peak here. And then the capacitor, as the signal is collapsing back to zero, the capacitor is going to discharge across the load. So the more capacitance that we have, the better the output signal across the load. So we got to keep that in mind. So capacitors are going to be connected in series, while capacitors are going to be connected, in parallel, as we're seeing here, while the inductor is going to be connected in series. Once more, remember, inductor opposes a change in current and is connected in series to the load and is connected before the capacitor, because the capacitor tend to have a very high current. So that way, the capacitor, like having the right amount of inductance is going to allow the capacitor current to rise pretty much in phase with your voltage. And that way, the voltage and current across the load is going to be in phase. And at the same time, by having this choke here, we are going to, improve or avoid like current spikes across the capacitor. And also this is going to improve the quality of the output voltage, because across the load, we are going to have a filter a filter DC output and a filter DC current output. Both of them are going to be filtered. Plus, everything is going to be in phase across the load. Any questions about that? Okay, so another common filter, like in electronics, is the pi filter. And you can see that this actually looks like a pi. And in this instance, we have like our capacitor, and then we have a coil and another capacitor. And the point of this is to be able to have like a very, very smooth signal across the load. By providing more capacitance, we're going to be able to have a way more smooth signal across the load. If you think about it, this capacitor is going to charge. This capacitor is going to charge. Once this capacitor is charged, it's going to be pumping that current through the choke in order to charge this other capacitor. And that's going to be causing our power factor across the load to be pretty much equal to 1, you know, to be able to achieve pretty much like a power factor or a phase component, and an in-phase component between voltage and current, which is going to be pretty much equal to 0. So you're going to have like a pretty nice neat rectifier. Depending on the amount of capacitance and the amount of inductance that you need, oftentimes it's going to be convenient to use like 2 chokes and 2 capacitors. And in this case, the choke input prevents large inrush current to the first capacitor when power is first applied to the circuit. And also it's going to be helping like the second inductor to filter the current. So because we have more devices, we're going to be able to have a much better filter. Like these last slides, like the IGBTs, we are going to talk about that, not right now because we're not going to use it. But as soon as we get into variable frequency drive, we are going to talk a little bit about IGBTs, because the IGBTs is the component that is mainly used for variable frequency drive. Okay, why is that? Because they produce a very smooth signal. They are able to turn on and off so quickly that they can produce kind of a smooth signal that resembles the sine waves. And that's what you want to be able to do in the case of variable frequency drive. Do you have any questions, guys? So something that I want to recommend you to do, okay, so this is the end of this little presentation. Something that I want to recommend you to do is that, okay, so let me show you here. It's like if I lost you. Are you still there?
I hear a lot of clicking, but
Yeah, we're all here.
Yeah, we're here.
Okay, that's good. That's good. So let me see. Maybe I lost. It's just that I'm trading my computer to get back to share my screen, and it's doing something crazy. Maybe here. Okay. Just bear with me for a second. Okay. Let's get back. So something that I want to share with you now. Okay, so in the workbook, there we go. I have the class already had the opportunity to do this yesterday. Okay, so the transformers that we are using, they have like 3 phases. Okay, so we have phase 1, 2, and 3. You're gonna go ahead and measure those voltages. Like the class yesterday found that those voltages is like 28 volts. So you have 28 volt on each individual phase. Each one of the phases, they have, okay, like 3 connecting points. They have 2
Or what
blues.
lab is this?
This is lab number 4. That's a good question. This is lab 4, the one that we are doing next. Okay, so we have 2 blue outputs, and those are the 2 outputs that we are going to use. So we have one in the center, which is white. I'm gonna put it black here because I cannot put it any other color. So this way we have like line 1. Okay, so between this line 1, we are going to be taking a power from the 2 ends. Okay, between these 2 points. We could say that we have line 1 in neutral for each individual one. And that's what we have right here. Each one of these is a line 1 in neutral. And then the neutral from the 3 transformers are going to be connected in order to form that Y junction point, which is where the 3 winding converge. That's the convergence for the 3 windings, okay? That single point that we call, or that we force to be a neutral. Okay, so something important here then, as we move along, of course, you are going to be able to see in this graphic here. And my recommendation is, even when we put these numbers here, you can always adjust these numbers as long as you write what is the scale that you are using for either your times division or your voltage division. You can use another scale if you want to. That's not a problem for me, as long as you have like a good, nice big graphic, and as long as you have at least 1 or 2 signals that are being displayed on the paper, on your paper, because that's what is going to allow you to be able to go back and see what was the amplitude and the magnitude of whatever signal that you were measuring at that time. Okay, so here, once more, we are gonna have that line-to-line voltage and the line-to-neutral voltage. So in Y, if the line to neutral voltage, let's say, was going to be 10 volts, how much is gonna be of my line-to-line voltage then? I have a Y system. If my line to neutral voltage is equal to 10, how much is gonna be my line-to-line voltage? Anybody can offer any suggestions?
0.7 square root of 3.
Yeah, we're gonna multiply by what?
Square root of 3.
17.3.
Perfect. Which is gonna be like 17.3, right?
Yeah.
So tomorrow, when you do this project, you have to make sure that between line 1 and 2, 2 and 3, and 3 and 1, you have, okay, the same voltage. And that voltage across from 9 to 9 is going to be a higher voltage than from 9 to neutral. So let's keep moving. All in all, okay, when you start connecting your rectifiers, first you're going to start, like, I don't have with me, but I'm going to show you in the shop tomorrow, that in the breadboard, I'll show you right here pretty quickly. But on the breadboard, you have the following. You get your breadboard, and on the breadboard, you have 2 sets of tie points that run horizontally. One of these is marked with a red line, and the other one right at the bottom is marked with a blue line. Do you remember seeing that before?
Yep.
Okay, so what I want you to do is that I want you to place your diodes. You see these diodes here? This here, that's gonna be your red line. That's what I want you to place your diodes. Along all these lines is gonna be placed across the red line on the breadboard. And that wire coming off the breadboard has to be a red wire because red means a positive output. Now the return wire, which is going to be connected to the center tap, Y center tap, that one will have to be which color wire? What do you think?
White.
Pardon?
White.
Okay, so in DC, like in AC, just right. In AC would be white, because in AC we have like black and white, black being the or red, red and white, black and white, and so on and so forth. That's in AC, but in DC, as we have in the meters, it's going to be like red and black. Black is going to be the negative terminal.
The
Okay.
line 2 going to your diode will be black as well.
Pardon me? The ones that go to the diode, that's a great question. Because we are using 3-phase and we want to be consistent, what we are going to do in that instance is that for line 1, we are going to use a red wire going into that diode. For line 2, a black wire going into the second branch diode. And for line 3, we are going to use a blue wire. That way, we never forget that the bridge rectifier that we are creating is a 3-phase bridge rectifier, but we have a red, black, and blue as the standard color code. Now, on the output side, we are going to be using red for the output positive, and black for the negative, because that's also the standard color code. Just like in your car, just like in the battery of your car, that you have the same thing, don't you? Okay, so any questions, guys? I just wanted to show you this, and I only show you so far the halfway rectifier, so you can assume, and you would be safe if you made the assumption that for the full wave, it's gonna be the same thing. However, like in the full wave, let me see if I can get rid of all this stuff here. I don't think so. Maybe yes, maybe I can. Okay, so for the full wave here, now we have our Y, as you can see in here, but the return, the negative terminal, this is the positive terminal, sorry. Okay, coming off the cathode of the diode, you have your positive terminal, but your negative terminal now is just the return anode of the other diode. So, and those two wires, of course, are going to be same thing. We are going to have for the positive a red wire here. And the reason we are doing that is because we don't want to get confused with positive and negative, because we're going to be using a capacitor that is an electrolytic capacitor, which is polarity sensitive. And if we screw up, we're going to have a bunch of oil in our faces once more, in spite of the chain of listening to the explosion and everybody looking at us. What's going on over there? Okay, so I want you to remember, please, that the positive terminal that we are creating from the diode is going to be a red wire, and then the negative terminal is going to be a black wire, which is going to be the return back into line 1, 2, and 3.
In the questions in that
Yeah.
at the end of project 4, it continues to ask what ripple output frequency is. How do we
Yeah.
find that?
Okay, perfect. That's a great question. So, okay, so let me show you before I let you go. So you will go here to page Roman numeral 9. Let me go back to that page. Okay, right here. So in Roman numeral 9, let's say, like if we have a half-wave rectifier right here, you can see that we have the cycles per second. This CPS is going to be your ripple frequency. Because that frequency, like pure DC, doesn't have frequency. The reason why we still get a frequency, that frequency is the frequency of the ripple voltage or the leftover AC that we have in the rectifier. And that's what you are going to use. For a half-wave rectifier, you are just going to multiply the line frequency. Like in this case, if your line frequency is 60 hertz, then you're going to multiply 60 hertz times 3, and that's going to give you 180 hertz. So you only have two choices because we are using 60 hertz. Either you have 180 hertz or 360. You're going to have more, you're going to have less. The only way you can have less is if you lose one of your phases and your rectifier gets into single phasing, in which case you have 120 hertz, just like in a single phase rectifier. Does that answer your question?
Yep.
Okay, so any other questions before I let you go, guys? So what I'm going to do, like, okay, Friday, please. Oh, well, no, not Friday, like next class, we are going to discuss, which is Monday, we're going to discuss any questions from the review questions that you have at the end of this chapter. We're going to discuss any questions that you may have any doubt about, in spite of the fact that I'm going to be posting like an answer key for those. Okay, so, but if you happen to have any questions after you see the answer key and you're still not sure, you are more than welcome to ask, and I hope that you are going to ask the questions. Anyways, I'll let you go because it's already 1:54. I have another class to go to probably, but I wish you the best, and I'll see you Friday, at least half the class.
I have a question. So you are posting the answer for those questions?
What do you say, pardon?
I mean, you are posting the answer for those questions or no?
If I have an answer key?
Yeah.
Yeah, I use.
All right.
But I'm gonna wait until after everyone goes through it this Friday.
Okay.
Before I post an answer key.
All right. Okay.
Yeah. Okay, perfect. I'll see you guys and Godspeed.